Thank you. Hello, everyone. Yeah, my name is Felix Schwock, and I'm a second-year PhD student in the ECE department at UW. And I hope in this talk, I get you interested in a novel approach for estimating neural communication that I've been working on during my PhD. Let me first start with some basic definition. Network-level neural communication can be defined as the dynamic signaling or exchange of information between different areas within the brain. And it is fair to assume that this is highly individual. So for example, two people, even if they perform the same cognitive task, will likely not show the same pattern of communication. Studying this is also relevant for neurorehabilitation, as baseline levels of neural communication might affect the outcome of a specific treatment. And finally, neural communication can also be used as a biomarker to assess the extent or progression of a disease or their associated treatment. So neural communication is important in the context of neurorehabilitation. But this begs the question of how we can estimate it. That is, how can we go from a set of spatially distributed measurements to a communication signal that describes the interaction between the different regions in the brain? And the answer is we need some type of model or modeling framework. But we don't want just any model. We want a model that can model some of the most important properties of neural communication. And those are, neural communication can be highly dynamic. For example, we might be interested in analyzing communication events associated with individual behavioral trials or stimulation pulses. Secondly, neural communication is mediated by an underlying network. For example, every signaling in the brain is routed through the underlying fiber tracts. And finally, it is useful to assume that neural communication is governed by some sort of mechanistic model, which can, for example, be expressed as a set of differential equations. And with that in mind, I want to get to the main part of the talk, which is the modeling framework. And this has been inspired by concepts from graph signal processing, which is an area that I'm very interested in for its potential use in neuroscience and neurorehabilitation. So to develop the modeling framework, let's start with a very simple mechanistic model. A simple heat diffusion process that is defined by the following differential equation. The first temporal derivative of the neural activity, ds dt, can be expressed by means of its second spatial derivative, as indicated here by the surface Laplacian, times a diffusivity parameter w. Now, this model can also be motivated from a neuroscientific perspective, as the right-hand side of this equation is essentially equivalent to the very popular current source density analysis. Now, let's keep in mind that in practice, what we have is a set of distributed and discrete measurements of neural activity. And I'm also assuming here that regions in the brain are connected via local connections that sort of serve as like a manifold through which the signals in the brain can travel. Now we can apply this heat diffusion equation to this discrete network setup, and we will arrive at the discrete graph diffusion equation, which can be written in this predictive fashion. That is, the neural activity at a certain node at time t can be predicted by means of its own past, plus the activity gradients from its neighboring node, each of them weighted by the diffusivity parameter w. And by incorporating only the information from the neighbors of I, we have effectively introduced the network in our modeling framework, which was one of our goals. Yeah, now you might have noticed that I've actually not talked about neural communication at this point in terms of this model. And for that, it is useful to remind ourselves that in electrophysiological recording setups, such as EEG or ECOG, the neural activity is recorded in forms of local field potentials, which have the unit volts. That is, activity gradients become voltage gradients, and the diffusivity parameter W can be interpreted as a conductivity parameter. Now, from elementary electrical engineering, we know that conductivity times voltage gradient equals a current. And so this means we can define our neural flow signal as this second quantity in the equation, the conductivity times the voltage gradient. And I will denote that signal as f of t in the following, and we'll call it neural flow. And you might see that the neural flow signal here has the same temporal resolution as the original neural activity s of t. And this is great because this way we can, at least in principle, model very dynamic communication events with very high temporal resolution. And I forgot to mention that the neural flow signal for the entire network is depicted here on the right by the black edges. Okay, but you might be wondering if a model that is as simple as that can actually model very interesting communication dynamics in the brain. And the answer is, at this stage, probably not. So we have to make the model a little bit more powerful. The first step is we can introduce eigendynamics to the nodes, which is indicated by this parameter mi here. Secondly, instead of using the global conductivity parameter W, we can introduce a spatially varying conductivity parameter. That is, each voltage gradient is now multiplied with a specific conductivity Wij. And the last modification is motivated by the fact that this equation describes a predictive model. However, currently we only use the time step prior to the current activity to predict the current activity. And we can extend that by using information from further in the past. That is, we can basically wrap this equation to a sum over the past p time steps. And this will, of course, also change our definition of the neural flow signal, which will now also include gradients from the past p time steps, each of them weighted individually by a specific conductivity parameter. And finally, I want to mention that the parameters mk and wk that constitute the model can be estimated from data using simple least squares regression. Okay, for the last few minutes of the talk, I want to show you some initial results of applying this model to actual neural recordings in the form of ECOG recordings obtained from monkeys following focal ischemic lesion. To get those recordings, my lab has induced stroke lesions in 4 monkeys using the photothrombotic technique. Afterwards, we have recorded the neural activity before, during, and after lesioning in the IPSI and contralesional hemisphere using 2 32 electrode ECOG arrays that are shown here at the bottom. And finally, in 2 out of the 4 monkeys, electrical stimulation was performed 1 hour after lesioning. Now, after recording the data, we use the data in order to estimate the parameter of this graph diffusion model, and then in the third step, compute the neural flow signal using the equation that I've shown 2 slides before. Now we wanted to answer the question, how does the flow, how does the communication change due to lesioning? In order to address that, we have computed the average flow magnitudes after lesioning and compared them to the average flow magnitudes before lesioning. And the changes in flow are shown here at the bottom left. So the blue edges indicate that we see a decrease in communication in the network due to stroke, whereas the red edges indicate that we can observe an increase. And as we can see in the IPSI lesional hemisphere, we can see mostly a decrease across the entire network, with a particularly strong decrease around the lesion location that is indicated by this black patch. In the contralesional hemisphere, on the other hand, we can see an increase through most of the network. Now, next, we have looked at the changes due to electrical stimulation in a very similar manner. That is, we have compared the neural flow after stimulation to the neural flow before stimulation. And we can see that in the IPSI lesional hemisphere, the neural flow only increases very localized near the stimulation location, which is indicated by this yellow flash here. But it does not increase across the entire network. And we were very excited to see that in the contralesional hemisphere, the neural flow increases localized in the area that corresponds to the stimulation location in the IPSI lesional hemisphere, but it also does not just increase across the entire network. And to see whether this pattern we can observe, the changes due to electrical stimulation, are unique to this model or can be uncovered by other more traditional techniques as well, we have compared them to results obtained from partial directed coherence, which is a statistical technique very commonly used in neuroscience. And when looking at the changes in neural communication due to stimulation for partial directed coherence, we see a very different picture, namely that the neural communication increases across the entire network. And on the other hand, for our graph diffusion model, we see much more localized changes, which we were very excited to see. Okay, to conclude and to relate back to the theme of the conference, I hope I have shown that computational modeling can be used to estimate network-level neural communication dynamics using this parameterized graph diffusion model. And it can also be used to characterize changes in neural communication due to lesioning and subsequent targeted stimulation. For the future, we hope that computational modeling can be further leveraged in order to develop more advanced techniques for studying neural communication, for example, by using nonlinear models, to study neural communication dynamics during behavior and individual stimulation pulses and analyze things like trial-by-trial variability, to predict the effects of a treatment on the neural dynamics and link that to behavior, and to account for individual differences in neural signaling to improve the personalization of treatment. And with that, I want to thank the audience for their attention and everybody in the lab involved in that project.
I have a few minutes for questions. That one right over there.
Thank you. If the model is based on the partial differential equations that govern diffusion, does that imply that all the nodes eventually settle on like an equilibrium?
Sorry, could you repeat the question? I didn't catch the second part.
Should all the nodes settle on an equilibrium, like a one in
Oh,
a
yeah, I see what you mean. If it would be a simple partial differential, a simple diffusion equation, and you would have it evolve over time, then yes, that would be the case. However, the way we use that model is essentially to transform the neural activity you measure in the different regions into a communication signal, essentially. So this is how you get basically a non-trivial solution that is not just essentially a constant signal across the entire network.
I see. Thank you.
Thanks for that great talk. So one really common challenge in trying to interpret network structure and neural activity is that we usually only measure a piece of the network. So can you comment on how your model is sensitive or not to the fact that we have a lot of unobserved neural activity?
Yeah, thank you. That's a really great question. And the honest answer is that I have not really had the chance to really study that, unfortunately. So the data I've applied it to are basically very localized, are small ECOG arrays, so they focus on a very specific part, in this case, the sensory motor cortex of the brain. But my hope is that the model in general can be applied to other data modalities as well that focus more on like whole brain imaging and fMRI signals. But this is something that I'm very interested in analyzing in the future if that works out. But yeah, unfortunately, I cannot give like a definite answer to that.
Thank you for the talk. I'm wondering, how does the assumption of communication by diffusion compared to, or how is that affected by communication via distinct pathways? So in the analogy from the diffusion equation might be, we also have convection through arteries, right?
Mm-hmm. That's a very good question. I haven't really thought about that very deeply, to be honest. So what I've realized is that this model, after you extend it to incorporating previous time step, it incorporates a couple of other physical models, such as it also includes a wave equation effectively. So you can use the same approach to model things like wave equation, which are then other dynamics, I guess. I haven't really looked at other more physics-based models that are closer or that are coming from a neuroscience background, I would say, but this is also something I would be very interested in exploring in the future.